Hey everyone, welcome back to The Explainer. Today we're diving into a pretty fascinating shift. In textbooks, transformers are usually presented as absolute perfection. Energy goes in, energy comes out, and there are literally no questions asked. It's perfectly efficient. But as we all know, when that textbook physics actually meets the messy reality of our real-world electrical grids, well, things get a whole lot more complicated and honestly, a lot more interesting. So think about it. What actually happens when textbook physics collides with the messy real world? Well, long story short, perfection completely breaks down. Today, we're going to explore exactly how engineers take these flawed, imperfect physical devices and mathematically tame them. It's a classic problem-solution story, really, where incredible engineering bridges the gap between those theoretical ideals and the gritty physical reality that actually powers our homes. Okay, let's dive right into this. Here's our roadmap for today. Number 1, reality hits the transformer. 2, unmasking the imperfections. 3, the exact circuit model. 4, simplifying the complex math. And finally, number 5, reflecting real-world impedance. All right, moving right along to section 1, reality hits the transformer, the limits of ideal models. So in an ideal world, every single line of magnetic flux would link perfectly from the primary to the secondary coil, right? And the wires, they'd be perfect conductors with absolutely zero resistance. But when we look at practical everyday power transformers, there are 4 major physical culprits that basically ruin our ideal model. We've got copper losses, leakage flux, core losses, and magnetization current. These 4 factors right here, they're basically our hit list for why a real transformer doesn't behave like the neat little ones you see in basic physics problems. Which brings us to section 2, unmasking the imperfections, finding the power drains. To really grasp this, we need to ask ourselves a simple question. Where is that energy actually escaping to? Well, first up is leakage flux. By definition, these are fluxes which escape the core entirely and pass through only one of the transformer windings. Think of it kind of like a pipe carrying water. Ideally, you want all the water to get from point A to point B. But in reality, you get tiny leaks along the way, right? Water drips out before it ever reaches its destination. In a transformer, not all the developed magnetic flux successfully links the primary winding to the secondary winding. So to account for this mathematically, we have to model it using primary and secondary reactance. Now, what's really wild to see here is how the leakage flux only links the turns of the coil that actually generated it. It literally just loops right back around its own wire out in the air. It's essentially wasted magnetic effort. It never actually reaches the other side to induce any power. And this perfectly illustrates the real consequence of that leakage. This stray leakage creates what we call leakage inductance, which in turn has a leakage reactance. Now you might be wondering, why does this matter to us when we're studying the grid? Because ultimately it causes unwanted inductive voltage drops across the coils. The net voltage you're actually getting out of the transformer gets dragged down by this leakage, which directly eats into the overall efficiency of your power transfer. Not great. Now, beyond the magnetic leaks, we also have raw physical resistance to deal with. These are our copper losses. The actual wires that make up the primary and secondary windings, they aren't perfectly magical conductors. They have lumped electrical resistance. As current flows through them, they just heat up. It's a basic resistive power drain, and we can model it simply by dropping a resistor into both the primary and secondary circuits. Okay, section 3, the exact circuit model, engineering a solution. So how do engineers actually take all those physical realities and map them directly onto a mathematical circuit? Well, take a really close look at the exact single-phase transformer model. On the left and right, in series with our lines, those components labeled RP and RS, those represent the copper losses we literally just talked about, just mapped straight out as physical resistors. And right next to them, the coils XLP and XLS, those represent the leakage reactance. So the physical flaws we just defined, they're now right there on paper as tangible, fully calculable circuit elements. But notice that parallel section dropping down right in the middle? That's the excitation branch. It perfectly accounts for the core's specific imperfections. We have RC, which models the core losses, basically the energy lost as heat in the iron core itself. And then XM, which models the magnetization current. That's the current needed just to establish the magnetic flux in the first place. So now our entire hit list of imperfections is fully accounted for in one exact, comprehensive mathematical model. Pretty neat, right? Moving on to section 4, simplifying the complex math, the approximate model. Now, while that exact model is incredibly precise, let's be real. Engineers absolutely love a good mathematical shortcut when calculations get overly cumbersome. So the absolutely crucial point here is this number, 2 to 3%. It turns out the current flowing down that middle excitation branch only takes up about 2 to 3% of the full load current. The vast majority of the current just bypasses it entirely. And this tiny little percentage, it gives us a massive, brilliant opportunity to simplify things. Here's the brilliant mathematical hack engineers use. Step 1. We formally acknowledge that because the excitation branch current is so incredibly small, practically negligible, we can treat it differently. Step 2. Because it's so small, we can just physically slide that entire middle branch all the way to the front of the transformer circuit. Doing this means we no longer have this messy parallel branch splitting our main series calculation right down the middle. It drastically, and I mean drastically, reduces the complexity of the math we have to do.
And here is the glorious after picture. By moving that tiny 2 to 3% current branch to either the primary or secondary side, we can combine our primary and secondary series resistors and reactances into single equivalent units. This approximate model makes computing real-world voltages, currents, and power losses so much faster and way more practical for everyday engineering. And the best part? We really don't sacrifice any meaningful accuracy to do it. Finally, Section 5. Reflecting real-world impedance, practical application.
So now that we have this beautifully simplified mathematical model, how is it actually applied out in the field? Well, the secret lies in a really fascinating concept called reflected or referred impedance. Because a transformer has a turns ratio, which we denote as A in our equations, we can't just add resistance across the sides directly. It doesn't work that way. Instead, we use a trick. We multiply the impedance by the square of the turns ratio. This clever move allows us to theoretically move the entire load from one side to the other right on our paper, letting us view this whole complex system from just a single vantage point. And exactly how we apply this model depends entirely on what our real-world goal is. If we want a step-down operation, the load is connected to the low-voltage coil. Think of power coming off the local grid straight into your neighborhood. But for a step-up operation, the load is connected to the high-voltage wind-in, which is exactly what happens right at the power plant before the electricity travels over those super long distances. In either scenario, engineers just reflect the impedance to the high side or the low side using our newly simplified equivalent circuit, and boom, they can solve the entire system instantly. So let's wrap this up with a thought. We started with this perfect, pristine textbook model. We watched it completely fall apart under the weight of messy physical realities like leakage flux and copper losses. And then we saw exactly how engineers hacked those real-world flaws into a beautifully approximated mathematical circuit. It kind of makes you wonder, doesn't it? If we can mathematically hack all these real-world imperfections into a neat, workable circuit, what else in our massive power grid is just a brilliantly constructed approximation of reality? Definitely something to think about the next time you flip a light switch. Thanks for joining me on this explainer. It's been an absolute blast guiding you through it, and I'll catch you in the next one.